Alrighty, good morning everybody. Welcome back to Math 105. Plan for today, finally going to discuss the classical laws of logic, / the laws of thought, however you want to refer to them. And this will finish off our discussion of Standard 6, which means for the next class, we'll be ready to start talking about Standard 7. I've got my usual office hours for the next 2 days, today and Wednesday. 10 o'clock and from 2 to 3. And tomorrow from 10 to 11:30 in the morning, 1:30 to 2:30 in the afternoon. As a reminder, you're certainly welcome, no matter what you'd like to talk about, whether it's because you're confused about something or you just have general questions, happy to talk to you in office hours. As far as homework goes, Standard 6 quiz is going to go up later today. And that I expect to make due on Wednesday. And exam 1 is going to go up tomorrow. So when I post exam 1, I will send out some detailed instructions for the exam. But like we talked about last week, you'll just be having to print out. You'll basically be responsible for kind of writing out and scanning in and uploading your exam solutions to Blackboard. Is the gist of it. So exam 1. So I was thinking about this weekend. I had budgeted out exam 1 as taking up each of the midterms is taking up class time in my preparations. So even though we're going to have it's going to be a take-home exam, I've decided we're not going to have class Wednesday. So instead, that'll kind of give you an hour during which you are welcome to take the exam. So keep that in mind. No class on Wednesday. Our next class will be on Friday. And on Friday, we'll start Standard 7. Any questions or comments before we get started for today? Yes?
There's no time limit on the exam.
There is a time limit on the exam, 1 hour time limit, but I'll be sending that out with the instructions.
Okay.
And that's, to be clear, 1 hour for actually working on the exam. That does not include time for things like printing out the exam and scanning and uploading your solutions. For those, I don't want to have to give you a strict time limit on something that's just tech issues. Other questions or comments? How can you tell if a clock is hungry? You can tell that a clock is hungry if it goes back 4 seconds. Okay, so in class last Friday, we had started Standard 6, which is kind of based around the notion of tautologies, contradictions, and contingencies, where we said that a statement is a tautology if it's always true in every possible context. We said that it's a contradiction if it's never true, that there's no context in which a statement's true. So a contradiction would be something like P and not P. No matter whether P is true or false, that compound statement, P and not P, is always false, making it a contradiction. And finally, we said that a statement is a contingency if it's true in some contexts, but not in all contexts. If I were to say, for instance, it is 4 o'clock p.m., that would be a contingency because, well, if it is at 4 o'clock, then it's true, but if it's a different time of day, then that statement would be false. It's a context-dependent statement. And we looked at several examples of these types of statements on Friday, both just kind of statements written out with specific examples, as well as kind of these more symbolic statements for which we're able to draw truth tables, to kind of get at when can these general compound statements can be considered one of these 3 things. And the truth tables allowed us to do that by sort of seeing if we had a column of all truths, that was a tautology. If we have a column of all falses, that was a contradiction. And if we have a column of some truths and some falses, that gave us a contingency. And so what I want to do today is kind of apply the techniques we looked at on Friday and start looking at some of the classical laws of logic, which ultimately, in a few weeks, are going to start becoming proof techniques for us. Techniques that allow us to kind of deduce and actually make logical arguments. And start off with there's sort of what's called the three classical laws of thought. The first is going to be the law of non-contradiction. So these three rules kind of date back to the time of Plato and Aristotle. Plato and Aristotle it's a little bit unclear which is which, kind of came up with these three different rules as being acceptable rules that every logically trained person needs to know and to be able to use in making rational, logical arguments. So the first one, law of non-contradiction, is translated from Aristotle as roughly saying one cannot say of something that it is and is not in the same sense at the same time. That doesn't look like the sort of statement we've been drawing truth tables for so far. Let's see. So what I'd like to do is to look at an example or two of this, just like what does this mean? How can we use this to say something useful? And then I'd like to then come up with a symbolic statement that says essentially the same thing as this, but using kind of the symbolic notation we've been working with. And then we can draw a truth table and see which of these three categories this law falls into. So one cannot say of something that it is and is not in the same sense at the same time. Where here, it is going to be referring, I think, to a mathematical statement. So an example of something like this, we could say about an apple, we could say, it can't be the case this apple is red and isn't red. We have an object. We can talk about a property that object has, namely an apple, and whether that property is being read or not being read. And one cannot say of something that it is and is not at the same time. We have an apple as our object. We can't say that it is read and isn't read simultaneously. What would be another example of trying to use this law of non-contradiction? Let's say we want to talk about this piece of chalk. What is something that we can't say is true and false about this piece of chalk at the same time?
It is white.
It is white. This chalk cannot be said to be both white and not white. Sure, that would be one way to use the law of non-contradiction, is to say we can't have something both have this property and lack it at the same time. So if we were to try and put a symbolic statement to the law of non-contradiction, to write it out using sort of symbols, let's say if P is going to correspond to object having some property. What do you think might be a way that we could actually construct a symbolic statement that gets at this notion that we can't have property P being true and property P being false of some object at the same time?
Could it be P implies not negation of P?
P implies not negation of P. Ooh. That's interesting. That's not what I had in mind, but I still like it. So basically saying P, if P is true, then we can't have the negation of P being true. Okay, I like it. That's one way that you could certainly interpret this law. It's sort of a symbolic statement that if P is true, it must be the case that the negation of P has to be false. So that in other words, the negation of P has to be true. What might be another way that we could write this if we were trying to say do this in a way that didn't use the implication symbol?
Negation of P and not P.
That's the one that I had in mind for this. That we're going to have a negation symbol of P and not P. That it cannot be the case, it must be false, that P and not P is true. And if we're saying that something like this is a I just gave it away. If we're saying something like this is a mathematical law, what are we saying about this? Is it true in all contexts? Is it false in all contexts? Or is it context dependent? Good answer, Dr. Gerstel. It's a tautology. It must. So our claim, when we say that we have this as a mathematical law, is that, well, for either one of these, however you want to state it, I'm going to go with the second one because that's what I had in mind. Our claim is going to be that this is a tautology, i.e., it must always be true that P and not P is false. So that's going to be our claim. What Plato and Aristotle are claiming is that if you have some property P, or if you have some statement P, then no matter what the statement P is, P and its negation cannot simultaneously be true. Meaning the negation of P and not P should be a tautology, or equivalently, what could we say about P and not P? The negation of P and not P being a tautology should be the same as saying what is true about the P and not P statement.
So it should be a contradiction.
That should be a contradiction. Both of which mean the same thing. That P and not P must always be false, or that its negation of P and not P, should always be true. And then, of course, if we wanted to prove either one of these facts, we could do that using a truth table. P, not P, P and not P, negation of P and not P, would give us a truth table that would allow us to arrive at this. So here, we only have a single base statement, P. If P is true, negation of P is false. If P is false, negation of P should be true. What would the column look like for P and not P in this truth table? Keeping in mind, if one is true, the other is always false.
It would be false, false.
I think it's going to be false, false. Because true thing and false thing evaluates to false. False thing and true thing evaluates to false. And so the negation would always be true. So here we can see P and not P is a contradiction. Here we can see that the negation of that is going to be a tautology. Here's the cool thing. When Plato and Aristotle were stating these laws of non-contradiction, one cannot say of something that it is and is not in the same sense at the same time. They did not have a nice symbolic way of writing that down. It wasn't for over 1,000 years later that mathematicians came up with this sort of symbolic notation. P implies negation, negation P, or negation of P and not P. That's notation that wasn't invented for over 1,000 years after, a couple thousand years, I'd say almost after the days of Plato and Aristotle. And so Plato and Aristotle were never able to say things like negation of P and not P is a tautology. They were never able to say things like, here's a truth table, because Plato and Aristotle didn't have truth tables. Here's a truth table, look, P and not P always false, not P and not P always true. Plato and Aristotle were never able to come up with these sorts of truth tables and help us kind of see this graphic of what's going on. They would just had to make general statements like one cannot say of something that it is and is not true in the same sense at the same time. Except, they said it in ancient Greek. Any questions about what this law says? Nito burrito. Let's look at another one. So our second law is going to be the law of excluded middle. Everything must either be or not be. Here's my challenge to you. I want you to think about what are Plato and Aristotle saying when they say everything must either be or not be. And my challenge to you is A, write an example, like we did with the apple in the previous law. And B, see if you can find a symbolic way to write that statement down. Let's go ahead and take a couple minutes. Think about this. As always, if you feel comfortable, you can talk to your neighbors. And see if you can come up with an example of this rule and a way to write it down symbolically. Is anyone able to come up with an example of a way that we could sort of write out the law of excluded middle using something from modern times. Or something from the time of the Greeks. I don't really care. What would be like an example of like the statement we could make about some type of object or person?
Apple must either be an apple or not be an apple.
An apple must be an apple or not an apple. That's actually leaning a little bit more heavily into the third law than I'd like, making a statement that's true about an object is itself. I'm going to change what you said very slightly and make it like just like a property of an apple. So how about an apple must either be red or not red? What would be another example? From this half of the classroom.
I either exist or I do not exist.
I either exist or do not exist. Sure. I, being a person, either have property P of existing or I do not have this property. An apple must either have the property of being red or it must not have the property of being red. Yeah, I think that's a great example. So both of these kind of get at are getting at the same core idea that if you have a mathematical statement about an object, either that statement has to be true or that statement has to be false. Something that we've sort of implicitly taken for granted since Standard 1. How can we break down the statement symbolically? If like P is our object or whatever having a particular property.
So I think this might be a little too complicated, but I had P or not P, like in parentheses, and negation of within parentheses P and not P.
Oh goodness, like that?
Then a negation in front of the second parentheses.
P or not P and not P and not P. Holy smokes. All right, do you have your hand up?
Yeah, I was just going to say P or not P.
Just a straight up P or not P? I think this is the one that I'd like to go with. Again, this is something I think that we could say has to be true if we were to combine the first two laws. That P or not P has to be true. Would be kind of what the second law is getting at, the law of excluded middle. And the claim that it has to be false, that P and not P is true, is more of a claim of what the first law is saying. But certainly, if we wanted to come up with a statement that says laws 1 and 2 at the same time, then we could make a statement that says something along these lines. P or not P and not P and not P. You're right, that is a bit of a mouthful. Yeah, I think P or not P is a great way to write out the law of excluded middle symbolically. And in particular, we're not just saying P or not P as a mathematical statement. When we make the claim that this has to be a law that always holds, what are we saying has to be true about P or not P? Which of our three classifications of statement are we saying P or not P has to have? Yes?
It's a contingency.
It's a contingency. It's true some of the time, but not always.
Oh, the law itself is tautology.
Yeah, I think we're saying that this law right here is going to be a tautology. That P or not P is a tautology. That no matter what your statement P is, P or not P has to be true. It has to be true that everything it either is or isn't. And if you want, you could draw another truth table for P or not P to illustrate that. We've seen that one a few times before. So if this is our law of non-contradiction, that negation of P and not P is a tautology, and our law of excluded middle is referring to P or not P being a tautology, what's the relationship between these two mathematical statements, P or not P, and negation of P and not P? Yeah, these are actually logically equivalent statements. The fact that the symbolic statements that create the laws of excluded middle and the law of non-contradiction actually come from saying logically equivalent things. That P or not P is always true, and negation of P and not P is always true. So our first two laws have logically equivalent statements. And it gets at the fact that they're referring to the same thing except with different thought sets in mind. For the first, and for the second, for the law of excluded middle, it's more of a positive mindset in which we say something has to be true. Everything either is or isn't. Whereas the first one is a little bit more of a kind of a negative mindset, the pessimist's version of the second law, in which we're saying P and not P has to be false. Things can't both be and not be, but things have to either be or not be. Any questions about these first two laws? Let's flip the page now and look at the third law. And the third law is the most interesting to me. And that's the law of identity. Whatever is, is. That's a sort of profound thing that makes you think, like, either the person saying this must be a genius or an idiot. And since we're talking about Plato and Aristotle and you're at Hillsdale College, you better not go with the second round. Or Dr. Arndt would storm in here and toss you out the window. Whatever is, is. Here's my example of this one. A rainbow squid is a rainbow squid. A chocolate bar is a chocolate bar. A cannibalistic Dr. Arndt is a cannibalistic Dr. Arndt. The way that I would write down the law of identity symbolically is by just saying if P, then P.
That's the same as saying P is logically equivalent.
Since we're referring to the exact same statement, yes. That would be another way of saying that. Because as we've seen before, like if you have two statements, P and Q, where if P then Q and if Q then P is the same as saying P and Q are logically equivalent. Here, if we're saying if P then P, well, we can also go backwards from the second to the first and still say if second P then first P, and that would mean P and P are logically equivalent. Yes. Yeah, that would be another great way to kind of look at this, is to say any statement has to be logically equivalent to saying the exact same statement. We drew a truth table. Truth table is as simple as it gets. P can either be true or false. If P is true, does the implication true thing implies true thing come out to true or false? Does the implication false thing implies false thing true or false? There's our truth table for it. The law of identity. I don't want to get too deep into a discussion of the law of identity today. But I do want to talk briefly about why do we have to have a mathematical law that says something that's so duh?
That's 2 steps that we would have proof.
Well, it's 2 steps. Well, it is something that certainly can be mathematically proven if we were to use the method of drawing a truth table. True thing doesn't imply true thing. False thing does imply false thing. So technically, again, we're saying these are tautologies. The reason why it's important, I think, to talk about the law of identity is because it's going to play a big role later in the semester when we talk about having a type of object that has this particular property. We're ultimately going to be making statements about things that have a certain property, and if we say they have a property now, we want to be able to say let's say these 2 lines are parallel. We want to be able to say that over and over. It's not enough to say these 2 lines are parallel, but maybe 10 seconds from now they're not parallel. We're going to be wanting to make statements that are of the form, if these 2 lines are parallel now, then they are parallel 2 steps later in the proof, 4 steps later in the proof. Once they have this property, they have this property. And that may not make much sense now, but it will be something that's going to be very important to us much later down the line. And so there we go. The 3 traditional laws of thought and logic. If you were a classically educated person, meaning you were an educated person during the time period I'm going to talk about, from the time of Plato and Aristotle all the way through to the Middle Ages, these are things that you studied in school. Law of excluded middle, the law of non-contradiction, and the law of identity. Because without these 3 seemingly basic tools, you can't make a rational argument, according to Plato and Aristotle. Every argument that you make has to ultimately lead back to one of these 3 tools. Any questions or comments? So if you flip the page, the next page, there's 2 more mathematical laws, the laws of modus ponens and modus tollens. And these don't date back to Plato and Aristotle, but they almost do. They actually come from one of Aristotle's students. It came from a guy named Theophrastus. And the law of modus ponens, simply put, says if P implies Q and P is true, then that implies that Q is true. And specifically, the law of modus ponens says this is a tautology. It's true in all contexts regardless of your P and your Q. If P, then Q, and P, then Q. So in other words, this would be like saying, if our property P is, this apple is red, And Q is going to be this apple is juicy. What the law of modus ponens is going to tell us is that if P implies Q and P is true, or let's say if these are both true, then Q must be true. So if we were, yes?
We have examples in our truth tables that say when the P can be true without Q being true.
Sorry, say that again?
Don't we have examples in the truth tables that say P can be true without Q being true?
Sure. But here we're making the assumption that if it is true that P implies Q, it doesn't always.
Oh,
In this case, I would say this apple is red and this apple is juicy are not necessarily one implies the other.
but if P and Q is true, or P implies Q is true.
Yeah. But if the implication P implies Q is true, and if the implication, or if the statement P is true, Q has to be true. So let's see if we can write out what does that mean here. If P implies Q, so if all red apples are juicy, and if this apple is red, then Q, then this apple is juicy. All that modus ponens is really saying is that if all P objects are also Q objects, and if you have an object that's inside of the P circle, then that object also must be inside of the Q circle as well. And our claim is that this law of modus ponens is going to be a tautology. That if all P's are Q's and you have a P, then you have to mathematically have a Q. Let's make a truth table for this. So, let's start with our kind of pre-filled columns for P and Q. We'll have our usual true, true, false, false, true, false, true, false. And I want to show that if P then Q and P then Q is a tautology, what other columns might be useful to construct before I get to the very end one? So we need columns for each of the individual pieces of this. If I ultimately want to be able to construct a column at the very end for if P then Q and P then Q, what might be a useful column to start with?
How about if P then Q?
Just P implies Q. Okay? P implies Q. True, false, true, true. Might also then just be helpful to have a column for if P then Q and P, which means we need to have a column for when is it true that both the P column and the if P then Q column both come out to true, which is going to look like a true, false, false, false. And then I think we could construct a column for if P then Q and P then Q. in which we're basically saying this column, when does this fourth column imply the second column? If the first column is true and the second column is true, then the implication is going to be true. If false, then false comes out to true. If false, then true comes out to true. If false, then false will also come out to true. In other words, we're going to get a mathematical tautology. Since this column is always true, P implies Q and P implying Q is a tautology. It's always true. So when we talk about modus ponens is going to be, other than kind of our truth table little proofs, where we prove two statements are logically equivalent, or prove something's a tautology, etc., through a truth table, modus ponens is going to be kind of a model for how can we sketch proofs. If we have some object, and we want to be able to show that that object has a property Q, one way that we can do that is to make a claim that, well, I want this object to have a Q, to be in the Q circle. I know it's in some smaller P circle, and everything inside the P circle is inside the Q circle. Therefore, we can use the law of modus ponens to say, I have a P object that I want to show as Q. Well, it's P, and all P's are Q's. If P, then Q is true. Therefore, it's going to be in the Q circle. Let's do modus tollens next. So modus tollens is another one of Theophrastus's laws. Modus tollens is going to be a law that says P implies Q and not Q implies not P is a tautology. So in other words, it's going to be it's a mathematical law that's making a claim in which we say, if P implies Q is true, and Q is false, then P must be false as well. Because if we have that P implies Q, and we have that not Q is true, meaning Q is false. If we have that if P then Q, and we don't have Q, then we can't have P. That's what the law of modus tollens says. Spoken graphically, if we have a P circle inside of the Q circle, and we're outside the Q circle, we must therefore be outside of the P circle as well. So this would be like making an argument that says something like, if where P is this apple is red, and Q is this apple is juicy, how could we write this argument out? If P implies Q is true and Q is false, then P must be false. How can we write out that argument in this specific example, where our statement P is this apple is red, and our statement Q is this apple is juicy?
If this apple, I'm trying to think about how to word this.
Wording's a little bit awkward on it.
If all red apples are juicy, and this apple is not juicy, then this apple is not red.
I like it. If all red apples is juicy, good job, Dr. Gerstle. If all red apples are juicy, meaning if P implies Q, everything in the P circle is in the Q circle, and we don't have Q, this apple is not juicy, then this apple is not red. Well put. If all red apples lie inside the circle of juicy apples, and if we have an apple that's outside of the juicy circle, then that apple must also lie outside of the red circle. Questions or comments? So, does this sound familiar? So, does this rule look like any of the rules that we talked about back in Standard 5? Where we talked about a relationship between if P then Q, and the relationship if not Q then not P. So, this is actually very similar to, what's the relationship, by the way, between P implies Q and not Q implies not P? We said not Q implies not P is the blank of P implies Q.
Contrapositive.
It's the contrapositive. And so, when we say that if P implies Q is true and not Q is true, then not P has to be true, we're really just saying, the modus tollens is really just saying, if P implies Q is true, then it's contrapositive. Not Q implies not P is also true. Because if all P's are Q's, and we have a not Q, then we must have a not P, is really the same as saying, if all P's are Q's, then all not Q's are not P's. Oops. No, I said with negation. And so, all of these classical laws, modus ponens, modus tollens, law of non-contradiction, law of excluded middle, law of identity, are ultimately going to boil down to things and properties that we saw from earlier in this packet and from Standard 5. They're just different ways of looking at these sorts of compound mathematical statements, and the laws are all just of the form, this compound mathematical statement is a tautology. Whether it's saying that if P then Q, then not Q implies not P, i.e. sort of this rule that an implication and its contrapositive are saying the same thing. Or if it's a rule like law of non-contradiction, which says you can't have P and not P, all of these sort of laws coming from Plato and Aristotle are really ultimately boiling down some logical property about statements P and Q that you can observe and make and prove using kind of more modern methods of drawing a truth table. For us in modern times, these sorts of statements are things that you can prove. For Plato and Aristotle and Theophrastus, these were not things that you can prove. These are just simply things that they noticed in making argument after argument after argument. And so while back in the day, you were just sort of expected to memorize all of these classical laws of logic, in modern times, we can actually go through and dissect each of these using kind of this method of drawing out truth tables and going through and analyzing each component of the argument. And that is kind of what we've been building up to in our first 6 standards, is being able to take all of these laws of logic and being able to analyze them and see if we can determine what are the circumstances under which these arguments must be true versus false. Okay, we'll finish off Standard 6 on Friday. In that case, Standard 6 quiz, I'll wait until next weekend to give it to you. We still have one more page in this packet, and I'm going to talk about how to make compound statements that involve 3 starting statements instead of just 1 or 2.
So you email us about the test?
I'm going to email the test, yes,
But no classes?
but no class Wednesday, correct? Thank you. You all have a good rest of your day. Take care.